Hello, this is 2015 paper question 2. So again, bit in the red, have a look, have a go first before jumping straight to the answers. Okay, this is another one where there's some descriptive parts at the top and the bottom, but then a calculation-y part in the middle. The first part, this is all about Poisson's ratios and the strains in different directions. The first part is an explanation of why you've got different Poisson's ratios with unidirectional continuous composites. I'm not going to go through this because it's all in the lecture notes. I've just copied the bit from the lecture notes in there. Have a look, have a go back to it, make sure you understand from the notes what the different bits mean, particularly in terms of what the definition of the Poisson's ratios are. But what I want to do focus on mainly is the numerical part, where what we have is we have a thin sheet of unidirectional composite, continuous fibre composite with various properties listed there, and it says we apply a tensile stress of 60 megapascals across the fibres in the plane of the sheet and calculate the tensile strain across the fibres. With all of these things, I always suggest drawing a little diagram. So what we've got here is our composite with all the fibres in the same direction, and we're applying a stress in that direction, 60 megapascals, and what will happen then is we'll get a strain in that direction, strain 2. We will also get some kind of compression, Poisson's contraction, which will be strain 1 in that way, and through the thickness we'll also get a bit of compression, strain 3 in that way. So those are the things that we need to work out within this question. It does it in bits. So the first one is the strain in the two direction. Now this is fairly straightforward because what we have here is just simple stress is modulus is stress over strain. So we know that the modulus in the two direction is the stress in the two direction divided by the strain in the two direction. Therefore the strain in the two direction is the stress in the two direction divided by the stiffness. So all we need to do is work out the stiffness in the two direction across the fibres. Going to the formula sheet in the exam, down at the bottom it gives us two different ones for the strain, for the modulus in the two direction. This one, the Royce model, which is the simpler one and doesn't work as well. So ideally use the Halpin-Tsai model, which is better and does work well. What we need to do in this case is work out this little value of eta, which is this function of the fibre stiffness, the matrix stiffness, put this into this equation to give us the value of E2. So I'll just copy that across just so we know what we're doing. And if we work the values out with that, the value of eta, hang on, I need to get that a little bit bigger. Get there in a minute. There we go. So the value of eta that we have here, work that out. I won't put it in, but it comes out to be equal to 0.9726. So that then means that E2 is given by matrix stiffness, which is stiffness of the matrix, tensile modulus of the matrix is 2.5 gigapascals. So that's equal to 2.5 times 1 plus 0.9726 times volume fraction of the fibres, which is a little bit higher up, lost what it was, 0.5. Sorry, I've lost that. There we go. Times 0.5 divided by 1 minus that. So 1 minus 0.9726 times 0.5. And if you work that lot out, that comes to equal 7.233 gigapascals. So what you can then do is to work out the strain in the two direction. It's just a case of, where's my pen gone? There we go. The strain in the two direction then is the stress in the two direction, which is 60 megapascals, divided by the stiffness, which is 7.233 gigapascals, or 7,233 megapascals. And if you work that lot out, it comes out to be 0.0083, which is 0.83%. So that's all you need to do for the first part, work out the strain in the two direction. Okay, the bit that then is a little bit more complicated is the next part, which is to calculate the values of Poisson's ratio 2:1 and Poisson's ratio 2:3 for the composite, and then use those with the same applied stress to calculate the strains in the one direction and the strains in the three direction. So what we need to do here is we need to remind ourselves a little bit what the Poisson's ratios means. So Poisson's ratio 2:1, what that means is it's minus, so that the terms end up as a positive, the strain in the one direction divided by the strain in the two direction. And the important bit with this is that the applied stress is in the two direction, because it would be different if it was the other way around. So what we can do with these is, if we wanted to work out the strain in the one direction, we know that the strain in the one direction is minus strain in the two direction times Poisson's ratio 2:1. And similarly, the strain in the three direction is minus the strain in the two direction times Poisson's ratio 2:3. So we know the strain in the two direction. If we work out the Poisson's ratios in both of these senses, we'll be able to work out the other strains. So all we need to do there is go to the formula sheet and find the formulas for these different things. But this is where it gets a little bit messy, because there's several different formulas we need. So if we're looking for Poisson's ratio 2:1, there it is, it's in that equation there. So we can use that one. Put that one there. But to find Poisson's ratio 2:1, we need Poisson's ratio 1,2 and E1 and E2. We've worked out E2, so we've got that, but we need those other two. So we then need the equations for E1 and E2 and Poisson's ratio 1,2. E1, hopefully we're all fairly familiar with this from law of mixtures. I can't find my pen. So E1 will just be VF EF plus VM, or 1 minus VF times EM, and putting the numbers into that, they're all given in the the question. That comes out to be 91.25 gigapascals. Poisson's ratio 1,2 is also actually quite straightforward, because that's given here, and it's another law of mixtures on the Poisson's ratio. So that one is quite simple as well. So in that case, we have it equal to, I can't remember what the numbers are here, 0.5, 0.2 and 0.35. So that's just equal to 0.5 times 0.2 plus 0.5 times 0.35. Check I've got my Poisson's ratio values right there. Yeah, that's right. And if you work that lot out, that comes out to be 0.275. So then what we can do is we can work out the value of Poisson's ratio 2:1. So Poisson's ratio 2:1 is equal to Poisson's ratio 1,2 times E2 divided by E1. Poisson's ratio 1,2 is 0.275. E2 we've just worked out slightly higher up. So that is equal to 7.233. So that's times 7.233 divided by E1, which we just worked out, 91.25, and that comes out to be 0.0218. So a much smaller value than the other one, but that was covered in the explanation in the first part. It should be smaller because of the constraint of the fibres. So what we can then do from that is we can then work out our value of strain in the one direction. So the strain in the one direction is given by minus strain in the two direction, which is 0.0083 times Poisson's ratio 2:1, which is 0.0218. Got that a bit wrong. Let me just 0.0. Let's do that properly. Times 0.0218, and that comes out to be a really quite small value, minus 1.81 times 10 to the minus 4. We could do an equivalent thing for the strain in the 3 direction. In this case now we need Poisson's ratio 2:3, so we can go to the equations. There's Poisson's ratio 2:3. We know E2, so that's alright, but we don't know G, so we need to work out G. The important thing to remember here is that all the G values are the same. So G23 and G in other directions and GC, we approximate them all to be the same. And there is a formula. Again, it's a Halpin-Tsai model for the value of G, which is here, and it includes this value of eta, which is the same kind of equation as the one for the tensile modulus across, but with the shear modulus instead. So if we, again, copy that. So what we can have here, in this case, the value of eta for the shear modulus comes out to be 0.9763. Therefore, the value of G comes out to be 2.617 gigapascals. So therefore, what that means, rearranging the equation at the top, Poisson's ratio 2:3 is equal to E2 over 2G minus 1. And if we put the values in there, E2 is 7.233, G is 2.167 minus 1. That comes out to be 0.382. So again, a higher value, but as the explanation at the top should have explained, that's to compensate the low value of Poisson's ratio 2:1. So the last thing that we then need to do is to put that together. So the strain in the 3 direction is now minus the strain in the 2 direction times Poisson's ratio 2:3. So that's minus 0.0083, which is the strain in the 2 direction, times 0.382. And that comes out to be minus 3.17 times 10 to the minus 3. So the fact that these two are negative, that's kind of explained because in our original thing, what we're doing here is we're applying a stress in the crossways direction, which will stretch the material that way. To compensate that, we'll shrink a little bit in the 1 direction and shrink quite a bit more in the 3 direction. So values all seem quite sensible. So nothing difficult in the maths. The complicated bit here is to understand what's meant by the different Poisson's ratios and to work your way through the different formulae, combining the values to make sure you get the right answers. The important thing with this is to make sure that you do the calculations slowly and carefully and try not to avoid an error that then follows through. If you do make any errors, please try and write clearly and put all the steps down so that I can see where you've made an error and can take account and give you most of the marks for just doing a simple calculation error. Okay, the last bit that we have then is what's meant by a symmetrical laminate and describe what advantages it has. Well, this is where we have laminates with different layups through the different fibre orientations through the layup, and a symmetrical one will have a reflection through the midpoint. So if we had a composite that had a 0° fibre, 0° layer there, it would also have a 0° there. It might have a 90 then going out from the middle. It then might have a plus 45 and then a minus 45, and on the other side it would then have the same plus 45 and then minus 45. So the symmetrical nature is that it's got this reflection about the midplane in terms of the layups. The advantage with it is that if we apply a stress that isn't along the fibres, we don't get any bending. So we get no bending stresses whichever way we apply a stress within the sheet. The other thing that we get is much less bending due to thermal expansion. So those things are important. And a couple of little diagrams for this would be very useful. It's only worth 4 marks, so it's not a great deal of detail needed.